that each point on that paper, it doesn't matter where, that each point on the surface is associated with a direction. Right? I want you guys to know that. And there's another diagram that it looks like this. I mean, maybe you see it from there, so I don't have to draw it. It looks kind of like this. The magnetic flux through a surface that looks like this, for instance, but this structure, it doesn't matter if you see this grid or not, it exists, or even on a blank paper, right? It's just to make visual that a magnetic flux through a surface, when the magnetic field is variable, relies on splitting the surface into small surface elements, which you see here or here, and it's even on a blank paper. You don't see it, but it's there, it's existing. So definition of the surface integral relies on splitting the surface into small surface elements. The definition of surface integral relies on splitting the surface into small surface element. Each element is associated with a vector of magnitude equal to the area of the element and with direction known to the element and pointing outward. Right? I will go in next video deeper into it. It's really just is fascinating. So I didn't know that it exists. So there is called in Wikipedia called the right hand rule, and you can look it up. I'm not joking. So I printed it out and read all the theory about it. But I think they don't know what I have discovered by a single theory, because I have a global theory that comprehends all these little theories what they have discovered. So the right hand rule looks like this. Remember I said to hold a finger, the rotation? Now check this out. So it tells you, it tells you the right hand rule is you hold your hand like this, you lay your pen, it doesn't matter left or right hand, you lay down your pen like this in your palm, and then it has this axis this way, and this way, and when you hold it, this is what happens. So this is right here, called the right hand rule. And let me read you the right hand rule. The right hand rule, it doesn't matter right or left-handed, the right hand rule pointing the thumb of the right hand in the direction in the direction, let me show a little bit here, in the direction of the conventional current, and the fingers in the direction of B, the force on the current points out of the palm. The force is reversed for negative charge. The direction of force. The direction of force on a charge on a current can be determined by a mnemonic known as the right hand rule. Using the right hand and pointing the thumb into the direction of the moving positive charge or positive current and the fingers in the direction of magnetic field, the resulting force on the charge points outwards from the palm. The force on the negatively charged particles is in the opposite direction. If both the speed and the charge are reversed, then the direction of the force remains the same. For that reason, a magnetic field measurement by itself cannot distinguish whether there is a positive charge moving to the right or negative charge moving to the left. And it looks like this. So it's you're holding your hands open, you put the pen, it's right here, in your hand, and this explains the right hand rule or the left hand rule. It's the same thing. Alright? I just want you to know, guys, that I'm not talking just stuff or bullshit or something like this. It's all true what I'm telling you. And another thing is this. There's something really also interesting. Now listen what I'm telling you right now. We know that the I, the letter I represents the person I. I also represents the center, and I also represents the ego in different kinds of fields, like the philosophical field, the psychological field, the I, the ego, the center, the starting point, whatnot. So it's the I. This is what explaining here. It's really incredible. So the current flowing in the direction of the right arrows, which goes up, which is connected, right? And the white arrow produces a magnetic field shown by the red arrows. So you see that? And the red arrows on the surface paper, when you write like this, electric current happens. So the I, the electric current, the letter I, the I, right? The I symbol was made by, is also a physicist, André Marie Ampère. The I, the conventional symbol for current is I, meaning current intensity. So I have the pencil that represents the I, upwards, writing on a electromagnetic field on a piece of paper by handwriting letters up and downs. The currency could be in a helix form or a spiral form or a coil form. By doing this with the pen, with this rotation, I create a magnetic field, electromagnetic field on a piece of paper to create energy onto it. All right. And if I go deeper, and I didn't know that, is that you. Let me read you something that you don't think I'm crazy or something. It's all in Wikipedia from physicists and mathematicians, that those algorithm called either the Maze algorithm, the Tremors algorithm, or the Pledge algorithm, and look what they say, what they speak, their theory. Just listen to it. The hand is removed from the wall only when both sum of turns made and a current heading are at 0. This allows the algorithm to avoid traps shaped like an uppercase letter G. You listening what I'm hearing? This allows the algorithm to avoid traps shaped like an uppercase letter G. You can look it up. Type in Maze algorithm, Tremors algorithm, Pledge algorithm on Wikipedia. The Maze algorithm. The wall follower, the best known rule for traversing mazes, is also known as either the left-hand rule or the right-hand rule, which I was explaining you, right? When you're holding the hand and you write. Is also known as either the left-hand rule or the right-hand rule. If the maze is simply connected, that is, all its walls are connected on the paper, all its walls are connected together or to the maze outer boundary, then by keeping one hand in contact with one wall of the maze, the solver is guaranteed not to get lost and will reach a different exit if there is one. Otherwise, he or she will return to the entrance having traversed every corridor next to the connected section of walls at least once. So, the wall follower, the wall is the paper. It's any kind of paper. It's the wall. The best known rule for traversing mazes is also known as either the left-hand rule, as explained you previously, or the right-hand rule. If the maze is simply connected, that is, as its walls are connected together, or the maze outer boundary, then by keeping one hand, like I don't have a table, one hand contact with one wall of the maze, The solver is guaranteed not to get lost and will reach a different exit in this one. Another perspective into why wall following works is topology. If the walls are connected, then they may be deformed into a loop or circle. Then wall following reduces to walking around a circle from start to finish. To further this idea, notice that by grouping together connected components of the maze walls, the boundaries between these are precisely the solutions, even if there is more than one solution. If the maze is not simply connected, if the start or end points are in the center of the structure surrounded by passages loops, or the pathways cross over and under each other in such parts of a solution path as surrounded by passage loops, this method will not reach the goal. Wall following can be done in 3D or higher dimensional mazes if its higher dimensional passages can be projected onto 2D plane in a deterministic manner. For example, if in 3D maze up passage can be assumed to lead northwest and down passages can be assumed to lead southeast, then the standard wall following rules can apply. However, unlike in 2D, this requires that the current orientation be known to determine which direction is the first on the left, on the right. And that was the maze algorithm, and then we have the pledge algorithm. And this is what happens, the handwriting. What I see in this algorithm is what happens when you write on a sheet of paper, and the process, how the direction, how you hold, how you do those loops, etc. It's very interesting. I will go deeper into it. And then we have here another positive and negative magnetic field upwards through the paper. And the thing is, those theories I picked up from Wikipedia, from doctor and physicists, they have all these little theories, particles, little theories, but what I have is the big theory that brings all those little theories together, you know. So I'm gonna make another video. Stay tuned. It's very, very interesting. Thank you for watching.